In this video, we are going to find real numbers x, y, and z such that the sum is equal to 1 and the sum of fifth powers is also equal to 1. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. Here is a pretty straightforward approach to solve this system. I'll just put the first equation into the second equation by rewriting the first as z equals 1 minus x minus y. Then put this into the second equation. We have x to the power 5 plus y to the power 5 plus 1 minus x minus y all to the power 5 minus 1 equals 0. So now we have a polynomial of degree 5 with two unknowns. Notice that if I replace x by 1, say over here, and then here, then the left side of the equation would be 1 plus y to the power 5 plus minus y all to the power 5 minus 1. And that's actually exactly 0. So that means x minus 1 has to be a factor of the polynomial at the left. We can use a similar trick and say that y minus 1 is also a factor. Now at the same time, if I replace x by minus y, like this, so the first two terms will cancel out, and then for this minus y, then for the last two terms we'll have 1 to the power 5 minus 1. So again, x plus y is also a factor. So now for a polynomial of degree 5, we've found out a factor of degree 3. So what remains should be a polynomial of degree 2. Notice that the polynomial is actually symmetric about x and y. So we expect to have symmetric expression of degree 2 of x and y. So the possible combinations would be we have some x squares and some y squares, but since it has to be symmetric, they should have the same coefficient. So why don't we let that to be a? And then we could have some xy. We can also have some x and y. So they should have the same coefficient. So let's say c times x plus y. And finally, a constant term. And so this should be the factorized form of the degree 5 polynomial. Now, the key is, how do we solve for the coefficients a, b, c, and d? Notice that we can actually treat the left side of these two equations as identical. So we can try put some numbers in for x and y and establish some equations about a, b, c, and d. To make things simpler for the time being, I'm going to put y equals 0, and then I'm going to put three values of x, 2, 3, and 4, so to establish three equations about a, c, and d. So here are the results by the computation. I've put x equals 2, 3, and 4, and y equals 0. So for the numbers over here, 30, 210, and 780, they are the results from this expression. And for the other side, I just replace x by 2 and y by 0, etc., and so on. So simplifying, we have three equations, three unknowns of a, c, and d, and we can solve it very quickly. And we have a equals minus 5, c equals 5, and d equals minus 5. And if we do something else, say if I put y equals 2 and then x equals 2 as well, then we can actually solve for b as well. So let's try. If we put 2 instead, then we'll have 64 minus 64 plus 1 minus 4, I should say, all to the power 5 minus 1, and that is minus 180. and that equals to 1 times 1 times 4, so that's 4 times 8a plus 4b plus 4c plus d. So 8 times minus 5 plus 4b plus 20 minus 5 equals minus 45. So b equals minus 5. That means we have this product, x minus 1, y minus 1, x plus y, and then minus 5x squared minus 5y squared minus 5xy plus 5x plus 5y minus 5, and the product equals 0. I can also divide both sides by minus 5, so we have either x minus 1 equals 0, which implies x equals 1, or y minus 1 equals 0, that implies y equals 1, or x plus y equals 0. This actually implies z equals 1, because the sum of x, y, z should be 1. And in fact, this actually matches the symmetry between x, y, and z. The final case would be, after dividing by minus 5, we have x squared plus y squared plus xy minus x minus y plus 1 equals 0. And for this we can split x squared into sum of 2 half x squared, and I will arrange them in this way. One of them, half x squared, would group with half y squared and xy to form a perfect squared, and then the rest would group with x and y respectively. And I'm going to also split the 1 as well. Then we can factorize each group separately. And then we have half of x plus y all squared plus half of x minus 1 all squared plus half of y minus 1 all squared. But that's impossible, because for each squared, there should be non-negative. The sum is 0, so that means each term is 0, but this implies x equals minus y and x equals 1 and y equals 1, but that's impossible. So no solution for this case. So after doing so much algebra, all we can tell is either x equals 1 or y equals 1 or z equals 1. But for each individual case, this just implies that the other two unknowns will have this relation, say y equals minus z, or x equals minus z, or x equals minus y. So altogether, our solutions are either we have one t minus t, a parameterized version, or y is 1 and the other would be t and minus t, or z is 1 and then t and minus t for the other two unknowns respectively, where t is any real number. So all of these are solutions to the system. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.